Mi deve pagare diritto. Facevo le scuole medie nel 79. Okay. So good afternoon. Please take a seat. We are going to start the afternoon session. Please come in. Okay, these sessions will be devoted still at a presentation of related to accelerators, future accelerator and state-of-the-art accelerator. And the first speaker is Daniel Schulte from CERN. He's the project leader for the design study for the future muon collider. And so this is also the topic is going to cover during his presentation. So please, Daniel, the floor is yours.
Thank you very much for this invitation. Unfortunately, I couldn't come because it seemed very sort of on the edge of with the conditions right now. It's really a pity. I would have liked to come actually. So let me talk about the muon collider. What I'm talking about is mainly almost 100% the proton-driven muon collider concept, which is a concept that actually has been developed in the past to a large degree in the US by the MAP collaboration. And where activities have also been done in the UK on a demonstration of the cooling principle that we will need in there. There was an alternative developed at INFN, Lemma, which looks very attractive. I will comment on that at the very end. But unfortunately, it seems that nature is a little cruel to us and that it requires parameters that are very, very hard to, if not impossible to achieve. So we will need some new ideas to make that alternative and a possibility. So the muon collider itself consists of a proton driver to produce proton piles, which you compress into one bunch or so with a very high number of protons. Then you send them into a target where you produce plenty of pions. And the pions decay to muons in the decay channel where you guide them and then you capture them. So you get your muon bunch. And then because the muon bunch comes from showers, it's a very hot bunch with a large emittance. And therefore you have to then cool it. And because you don't have much time, because the muon lifetime is limited, it's only 2 microseconds at rest, then increases with energy, you have to do the cooling in a novel scheme in matter by ionization cooling. You cannot use a damping ring or any of the more conventional tools. And after doing that, after cooling the beam, you accelerate, and you have to do that also rapidly in a LINAC, recirculating LINAC, a sequence of rings, there's only one shown here, as quickly as possible to high energy. And then you inject into a collider ring, which you make as small as possible by using the highest field magnets that you can afford in order to get as many collisions out of the muons before they die. We think that this is a unique opportunity for high energy lepton collisions with the muon collider. So there's an international collaboration that is forming. Actually, INFN is a member of that collaboration. But the objective is, the near-term objective for the next European strategy to provide the material to establish whether the investment into a full CDR for a muon collider and into a demonstrator program is actually justified scientifically. If then the strategy, the European strategy supports that, at which timescale or so, that will depend on other things as well. And for that, we will focus on 2 main energies. One is the 10 plus TeV which is why you would do a muon collider, because it's the sort of a really high energy, and we need high luminosity there. And then a 3 TeV stage that could be seen as an intermediate step and would probably be done with technology that can be more readily available in a shorter time scale. And it would also split the cost. We think it might be half the cost of the 10 TeV collider for the 3 TeV collider, but we have to establish that more. We will also look into neutrino or Higgs factories as synergies, but that's not really the main goal of us, and define the R&D path. This is done in a sort of broad international collaboration. Here, these are community meeting conveners. So not all countries, or not institutes from all countries can sign the MOC. You know, like in the US, it requires the P5 process to conclude, and then it will still be difficult. You can see that there are plenty of conveners from all regions, many from Europe, but also from the US, from Asia, China, and Japan, mostly participating and organizing the meetings that we had. So what do you need at high energy? I mean, lepton collisions at high energy give you two big advantages. One is you can use them as precision machines, like lepton colliders typically can be used for that. But you also get discovery reach potential, which is reasonably high because your leptons carry the full energy, unlike a proton, where actually the energy is split over a number of particles. And therefore, normally you don't have the full energy available for the production of new particles. So here you see a comparison where on the horizontal axis you have the muon or lepton, E plus E minus would do the same, center of mass energy, and on the vertical, the equivalent proton center of mass energy. This comes from Andrea Wulzer. And you see that, for example, a 14 TeV muon collider correspond to 100 or maybe even 200 TeV proton-proton collisions. This depends on the model, and certainly with different physics, these curves look different. One of the issues that occur at high energy is that you also need high luminosity, because the cross sections for the S channels, so for the central collision, go down as 1 over the center of mass energy squared. So what you need is a luminosity that increases with the center of mass energy squared. So squared of S is the center of mass energy, and with that squared with energy. So you have a luminosity challenge as much as an energy challenge. And if you look at this goal, which comes from the theorists, you see that Click actually would achieve that goal at 3 TeV. It would be a factor 3 above, but actually there's Beamstrahlung, so 1/3 of the luminosity is really at full efficiency. And so we see that this curve seems to make sense. Now let's look at why could muon be interesting. So first we have Click, which is the highest energy lepton collider proposal that has been thoroughly studied with the CDR. And you see here in red, this is the luminosity that Click can achieve as a function of beam power. And you normalize the luminosity to the beam power, sorry, it's a function of center of mass energy, and you normalize to the beam power. So you see that a linear collider, and you can theoretically predict this should be the case, has a constant ratio of luminosity to beam power independent of its energy. And that comes from Beamstrahlung and actually your ability to produce high quality bunches at different energies. It assumes that beam quality does not degrade towards high energy. Click at 3 TeV, you know, costs 18 billion Swiss francs and uses about 600 megawatts of power. So it's quite ambitious already. In contrast, if you look at the muon collider, and you also look at luminosity divided by beam power, you see that this ratio is increasing. So you get more luminosity as you go up in energy. It should rise linearly, and we think it actually continues beyond the 6 TeV. These are map parameters, which I show here. So at high energies, the muon collider potentially offers significantly higher luminosities for the same beam power, and we think that translates into better efficiency that we have to do detailed studies on to be sure. And we also hope that the muon collider actually at higher energies is more cost effective than other approaches. But also that needs to be verified. It just can be concluded, and looking at the scale, the size, that this might be expected. Let's look at the specific luminosity goals that we have for 3, 10, and 14 TeV. Actually, we are studying 3 and 10, and 14 is more like an exploration. Maybe we will even look at 30, but we don't do any promises there. We really design for 10. And we have 1 inverse autobahn at 3, 10 inverse autobahn at 10, and 20. So it scales with the square. It should be 0.9 inverse autobahns at 3. We rounded that up a little bit. Maybe that's a bad idea, but we did that anyway. Here you see the parameter sets, which we get by scaling from the map study parameters. So we have to then verify that this can indeed be achieved with a realistic design. So that's what we have to do in the next few years. And you can see the luminosities here. They would be consistent with getting this integrated luminosity within 5 years, because we operate a bit more than 10 to the 7 seconds per year, effectively 1.2 10 to the 7 seconds, like the click and FCCHH effective time of operation per year. You see the bunch charges, 2 10 to the 12, 5 Hertz repetition rate of producing bunches, and then they collide a few thousand times in the collider ring. And the beam power, you see that even at 14 TeV, it would be only 20 megawatts, while click at 3 TeV already needs 28 megawatts. So this is indeed here showing the potential advantage at high energies, because with that achieved the luminosity goal from the physics. And you see one of the problems that we will have to face is that as we go up in energy, the bunch needs to become shorter and the beta function to be also smaller in order to achieve this goal. But we still stay with spot sizes of the order of a micrometer. So, okay, so that's the goal. And now we will see what are the key challenges to go there. One is actually the physics case, because that really needs to be studied at 10 TeV. It has been studied thoroughly at 3 TeV, but going beyond that and needs more effort, because you can always find new things also that can be done. Then there is the beam-induced background at the collision point. I'll come back to that. It's because the muons die, they produce background. There is a dense flux of neutrinos coming from the collider ring that needs to be mitigated. I mentioned that. The high energy complex, you see actually that the accelerator ring is larger than the collider ring. This is not to scale, because here you have to ramp the magnets in the accelerator ring with the beam energy, while the collider ring that is superconducting at highest field. And so the cost and power consumption of the accelerator ring are, for example, very important. And then losses by decaying muons in the cold magnets of the collider ring are also maybe limiting the energy reach via cost and power consumption. And then the source of the muons with the high quality beam, certainly a challenge. Much has been done on this in the US, but I think there's need and room for improvement. So let's go through the complex very rapidly. The proton complex, the beam power of maybe 2 megawatts, that's the current estimate, is not a problem. You know that more will be done at the ESS and the SPL at 5 megawatts planned. Then you need to actually accumulate the bunches in a ring, bunch them really, and combine them to have a very short high intensity proton pulse. That is some challenge. We hope that is manageable, but we will have to look into that in more detail. Then you have the target where you shoot. This here is actually a fluid mercury target. We probably cannot do that in Europe anymore for safety reasons, but we could use a gallium or actually a graphite target. And so you shoot the protons in here, but since it's a megawatt proton beam, you get radiation around, and you need a solenoid which guides the muons, first the pions and then the muons, in longitudinal direction. And so you need thick shielding to protect this superconducting solenoid, and you need a large aperture because shielding needs to be thick, and you need a high field in order to squeeze the beam down as much as possible to make it as cold as possible initially. So that is a big challenge for the magnet. After that, you cool, and the cooling is a very simple but unique process. You have here, as you can see, a muon with a transverse and longitudinal momentum. You go through matter, and you lose energy or momentum also by ionization. So you reduce transverse and longitudinal momentum, and then you accelerate in cavities, and you just gain longitudinal momentum. So the transverse momentum shrinks, and your beam cools. Now the problem, this would be no big problem as such. You would like high gradients, obviously, to make the system short, so you have fewer muons that die. But you also need to do this in a high magnetic field because you have multiple scattering. And the higher the field, the smaller the impact of multiple scatterings on the beam. And that also means that you need not only the highest fields here, which is challenging solenoids. We actually would like to have 20, 25 Tesla. The US study had 14 at the maximum. But we hope with the HS we can do better. But also this field will extend over the accelerating cavities. And that is a unique thing that normally you would like to avoid having field there. So a proof of principle has been done of these cavities, but obviously this needs to be developed, and we need to do more experiments on that, developing different approaches. So the challenge here is to have many of these magnets, and then at the very end, we have to increase the field more and more, and you would like to go well beyond the 30 Tesla that has been already demonstrated, and maybe go up to 50 if we can do that, as high as possible. Luminosity will be proportional to the field. Okay, so that's there. So that's very unique, and the RF also is very unique. In order to achieve these high fields, it's normal conducting cavities which have either beryllium end caps or which are filled with high pressure hydrogen, and they achieve like 50 megawatts per meter with frequencies of the few hundred megahertz. Now, this principle of ionization cooling has been shown with quite some struggle for different reasons in the UK. So this is the setup. You have muons coming from the left. You have a solenoid, and in the middle of the solenoid, you can put an absorber, and you measure the muon beam a bit before and mainly after. And this is on the right-hand side, the extra side. And now what you can see here is, if you look at the upper plot, that's one of the many experiments they did. The distribution of the muons before they go through the place of the absorber. You can see that here in brown. And then downstream, if there's no absorber, you see the green curve. You have basically the same amplitudes, and larger amplitude particles get lost on the way. So actually, it's less there, but you can see it's essentially the same shape. Now you put in the absorber, liquid hydrogen in this case. And what you can see is that before, I mean, the brown curve does not change, but the green curve changes. You have more muons at low amplitude now, and some less at higher amplitude. Here, actually, it doesn't change so much because it's fed from sort of the ones that would have been lost in the upper plot. And so you can see that muons actually populate the small amplitudes more, which comes from the cooling. And so that principle has been established, but it hasn't been done with the RF, and obviously there's quite more that should be done. But the principle is sound, and actually it seems to agree with the simulations. Now, the next challenge is the high energy acceleration. And the problem there is, okay, there are Linux, and you have a high beam loading because the RF system, we have a high bunch charge, 10 times the high luminosity bunches to have a comparison. So it's important single bunch effects. But then there is this accelerator ring, or rather a sequence of those. And the default option for that is to use an pulsed synchrotron, rapid cycling synchrotron, but it's not really sort of like a sine wave pulsing. It's really oscillating, it's really pulsed. And so you use normal conducting magnets that you drive up in the field. And actually, in order to gain more reach, you power these normal conducting magnets first against bending the beam in the right direction. You have a few superconducting magnets interleave with the normal magnets so that they bend the beam. And then you ramp the normal magnets down and up on the other side. And by that, you double the effective range they have. And this ramping needs to be done in milliseconds. And so we need a kilotesla per second ramp rate. And we need a huge stored energy in the magnets on top, which means that the power converters need to store this energy, pump it into the magnets, and then take it out of the magnets with a very high efficiency. We cannot afford to lose a significant fraction of the energy in the system. So we need to be more than 95% or so efficient. The RF system, as I said, is very challenging because it's a single high charge bunch. And alternatively, one could consider using an FFA, where you have fixed field magnets that could be superconducting, and you have a very large energy acceptance of a few 100%. That's very challenging also, and probably also expensive because you need a significant length of superconducting magnets. So that's the main challenge of the acceleration. Actually, I should show there have been like a proof of principle fast ramping magnets looked at the US, but the efficiencies and the power and the cost of that system, that really needs to be developed because that's the longest system of all. And interestingly enough, superconducting HDS magnet achieved like almost 300 Tesla per second, which is on the edge of what we need in the last accelerator ring. So we are not so far from being able to maybe use HDS. In the collider ring, you need very high field dipoles because you want to make the ring small. Now, we assume that for the 3 TV, you would use only like 11 Tesla dipoles, something more on the high luminosity LHC level, because it should be faster. And then at 10 TV, one would go to the highest field dipoles that one can assume, maybe 15 Tesla or so. That we will learn from the magnet roadmap. One of the challenges then is that because the muons decay, they produce 2 neutrinos each, and then 1 electron or positron, depending if it was a mu plus or mu minus. And that electron or positron carries roughly on average 1/3 of the energy. So you lose about 500 watts per meter from dying muons in the ring, because the whole beam dies somewhere in the ring. And so you need some large aperture. There was a design with 15 centimeter aperture. Actually, there were designs with smaller apertures. We are just re-evaluating if really 15 centimeters is needed. Because now you need to put in some shielding so that your superconducting magnet does not intercept the 500 watts, but maybe only sees a few watts. And so the S study showed that this is possible, but we have to really see how much shielding is needed and can that be improved. We hope at higher energies this doesn't become so much worse because the shower depth is not increasing that dramatically with energy. Okay, then we have the focusing at the IP, and that needs to become stronger at higher energy because we need shorter bunches as we go up in energy. So the beta function goes down as 1 over the energy. At 3 TV, we have a design from the map study you see on the right-hand side, which has up to 12 Tesla maximum field in the aperture of the quadrupoles. So it's similar to LHC, high luminosity LHC, which has up to 11, a little more than that. And the apertures are also similar to high luminosity LHC. So once that problem is solved, as we hope it will be in a short while, that should work. At 10 TV, certainly these magnets become more challenging. You need, because the beam becomes stiffer, you need larger gradients and also larger apertures, we feel. But that will be on the somewhat longer time scale. Okay. Now, then there's the problem of neutrino, of the neutrino flux. It's a very annoying thing. It becomes, we produce these 2 neutrinos, as I said, when the muon dies. They go into a very small cone with an opening angle of roughly 1 over gamma. Actually, the effective equivalent angle is 1 over 1.1 over gamma. And these neutrinos go through Earth, no problem. So they come out of the surface of the Earth somewhere. And unfortunately, their probability of interacting with matter is not 0, but it's very small only. So with a very small probability, they start to shower just before they leave the Earth or just after, and start to initiate a shower that can produce some radiation. Now, certainly our goal is to make sure that the machine will never impact the environment more than LHC does. So the goal is to stay at the level of the LHC, which means that actually there is no radiation outside that requires any approval. The goal is not to stay below what can be approved, but rather to stay below what does not need an approval at that location. Maybe then at some locations we still need approval, but now we understand that for 10 TV, we actually need some mitigation technique for this neutrino flux. And the proposed method from MAP was to actually move the beam within the aperture. However, you can see that this gives you only a limited improvement. And so our idea would be to actually deform the beam line. So you see here a part of the arc lattice, and you see that this has a sequence of parabola. It's not a sine wave actually, because parabola, because we want a distribution that is equal in angle. And then what you do is you, once in a while, every few hours or so, you move the node of this pattern a little bit to the left. So you need to cycle through one of these 600 meter long waves, if you might call it like this, once per year in principle. And by this cycling, then you see that the pointing vector at each location changes in the vertical direction, and by that you actually dilute the neutrino flux. And with that, we think like a 200 meter deep tunnel would be good enough for 14 TV. Now that's beam, certainly we need to understand the beam impact on the beam operation and on the hardware. So that's one of the goals for the next few years. Then there's the physics potential and the MDI. So for the physics potential, I will not say very much. Our theorists get quite excited about the physics potential, so it might be worth to have a dedicated presentation some other time on that. Not within this frame, certainly. But the machine detector interface, the MDI, is very important. And the reason is that when you produce this high energy electron or positron through the muon decay, then actually that can be lost because it's off energy in the interaction region. And we produce something like 40,000 muons per meter and bunch crossing in the 14 TeV case. If you go to lower energies, it's more decays, but with less energy in each decay. So the total energy per unit length, the 500 watts roughly, is the same independent of energy. Then there's also beam background that we are developing, but these decays occur all the time from the beams, so that's a relevant one. And so then you have to place masks in the detector that actually stop all the secondaries from entering the detector. You still have certainly a few that decay either very close to the IP or where you have things that go through the masks, a small likelihood, or that bounce through this inner part here. You see that, I mean, there needs to be an opening for the beam. However, what we see is that these rates are reasonably low, and there is an active group actually at INFN looking into the impact on the detector, and they conclude that it may be quite manageable, even if it puts very strong constraints on the hardware. So, for example, you use timing because these secondaries come off time from the IP, because like they bounce off the mask on the other side and then come back, and they also come from the wrong direction. So the idea is to use that. So that looks good. Now, in order to see what should be done on the Muon Collider, you probably are aware of the European XLHRND Roadmap that has been worked on in the past year, and that will be presented to Council next week. And so this consists basically of the LDG, which is the Laboratory Directors Group, which includes actually INFN, to develop the roadmap, looking at magnets, plasma acceleration, RF, muons, and energy recovery Linux, and then to write a report with the proposal of what should be done that is given to Council. For the Muon Collider, you see the members of the panel here. And if you want to look up more, there is a link. Now, the report is still confidential, even if maybe more is known about it than, so I can only give you my impression of the discussions that we had within the panel. And the conclusion there seems to be very much, and we had critical people, I mean, like Thor Raubenheimer was there, Philippe Lebrun, Mike Seidel, so we didn't have just people that were in favor of the Muon Collider. So the conclusion there was that the Muon Collider has a high potential for the physics case. It is not as mature as other lepton collider options, in particular CLIC, which is the highest energy lepton collider. I mean, there's a 3 TeV CDR out there in the project implementation plan. So that's really the benchmark the Muon Collider has compared to. If it cannot do better than that, then it's worthless. There are many challenges and severe challenges, but none of them look like showstoppers. So we think that all of them can be overcome, and that there is a way forward, which is to do a intense R&D program. I'll come back to that in a moment. And this would require certainly a potential ramp up actually now and in a few years, depending then on the European strategy, on the needs of the strategy at the time when this needs to be implemented. So we also debated about timelines. Now, for the Muon Collider, it's clear it's interesting in the very long run because it seems a very promising way to produce high energy and high luminosities, which for lepton colliders will be useful at any time scale. I mean, even if you imagine that the FCCHH would have been built starting 65 or something in the next century, the Muon Collider could still be of interest. However, the Muon Collider could also serve as a shorter-term fallback case. If, for example, the Higgs factor is not realized in Europe, then Europe is looking for another project, I would suspect. And so the Muon Collider, we try to make sure that it can be an option for the next big collider project in Europe after the LHC. This would be a 3TV option, and we would have to make compromises to realize it on such a time scale. But we came up with a schedule where we would have the design of a demonstrator until the next European strategy, which we assume would take place in 26, and do a baseline design and some modeling and some prototype preparatory work. Then with the next European strategy, there would be a decision process after, and if the Muon Collider were to be done at high priority, high speed, one could build a demonstrator starting in 28 or so, because more resources would become available maybe 2 years after the European strategy starts, but some prototype would already work would already happen during that period. And then in time for the European strategy after, there would be first results that could actually give you enough confidence that you can commit to the project. And then one would make a technical design and go into construction. Now, this is technically limited. Construction, sort of the beam could be switched on maybe in 44. All decision-making processes will have a tendency to delay this at some level. But technically, this is an aggressive but not excluded timeline. What is now the way forward in the near future? So the physics case needs to be developed, but that's not part of what I will cover. And we need, we proposed an ambitious program in the roadmap, which includes design of key accelerator systems to make choices and define what is needed. And then transfer technology developments that happen like on magnets or RF, and address specific technologies that are Muon Collider specific that we can only do in collaboration. That covers magnets, RF, machine detector interface, these fast ramping magnets, neutrino flux. So the design of a cooling module, I go back into that, and absorbers and targets actually also. So for magnet development, the European roadmap for magnets is of interest and importance to us, especially because of HTS development. We think that this is a very promising part of this development. We need dipoles and quadrupoles, where for the 3TV we try to be more conservative, more in line with what the Halumi will hopefully have demonstrated at the time. And for 10TV, we would assume that we probably have performance parameters more like what FCCHH is pushing for. But we will know more about that thanks to the magnet development in a few years from now, and the translation to the Muon Collider. For solenoids, we actually have more demands. That's rare in accelerator physics. We need very high field solenoids, the highest fields that we can achieve. And the target solenoid is an engineering challenge, similar to a detector solenoid, actually, in terms of stored energy and so on. And we also would like to improve compared to the S program by using HTS instead of Novum 310 for the majority of the cooling. There are a few, like 1,000 meters of cooling. And then we need to address, obviously, the ramping magnets and their powering, because that's the longest system in the whole collider. And so that could be having a severe impact on the power consumption and the cost. And we talk about a few, like something like 10 gigawatts of peak power going through these power converters and the magnets, and it's something like a gigawatt on average, which means that the efficiency, that's why it needs to be so high, so that we have only a few tens of megawatts of power consumption for that. Neutrino radiation mitigation, we need to understand that these systems to mitigate the neutrino flux are robust and can work, would be reliable enough. We need a very good accurate alignment, because we have to make sure that where we are pointing to on the surface even, and we need to understand that the beam operation is possible with all this. For the muon cooling RF, this is really unique because it's this gas-filled cavities in a high magnetic field, or could be also vacuum beryllium. And we need to go from 2 proofs of principle that have been done in the US to more practical cavities, and we actually need to test these things. Like there was the idea to use cool copper, so copper at 50 to 70 K, which would be better maybe than normal copper, but we have no idea whether or not in a magnetic field this works. And there is no test stand anymore in the world, so we need such a test stand to develop the RF. Superconducting RF also needs some further development. At the high energy we have that. especially looking at the beam loading with short bunches. The target, because it's certainly a very ambitious target for the muon production, pions first and then muons, and the shielding and the collider ring, and actually the absorbers, for example, also in the cooling, the windows of the absorbers, this type of thing. The cooling cell itself, we would like to develop, which is an engineering design challenge. You see here an example of a cooling cell at the beginning of the cooling with a large aperture solenoid and an RF cavity and the absorber here. And then towards the end, you see something where we have actually a much higher field, a smaller aperture around the absorber and your cavity inside. And you see the VS design had 13.6 Tesla here. We would like to have more. And that's really an engineering challenge, just to make sure that all of this is reasonable. Here we can already see that there is not enough space, I think, between the cavity and the solenoid. So that needs to be worked out in some detail, because the devil here is really in the detail that needs to be taken into account. We also consider the demonstrator, which mainly would be a facility to demonstrate the cooling of the muons. So we would use a proton beam, send it into a target, produce muons, and then we would collimate the muon beam to a small emittance and prove the sort of a smaller emittance part of the cooling chain, not the large emittance initial part with a higher intensity, but rather with a lower intensity but very small emittances towards the end, and then actually a module maybe with a proton beam or so with high intensity. We have a sketch of how much space would be needed. So here you see we would have a target, maybe with a horn or with a superconducting solenoid. The horn is cheaper, solenoid more performant, but more expensive. And then we would select the energy. We would have some diagnostics. Then we would have a cooling section, and then some diagnostics downstream. And this needs to, in total, a bit more than 100 meters, of the order of 100 meters. And we looked at place for that. And for example, at CERN, there would be a site outside of the CERN boundary, but on CERN land. So CERN owns this spot here. It is where the PS2 would have been built. So you see we can have a beam injected from the PS here. And there is enough space for such a test facility. And you could even dream if you would want to build something like Newstorm or so, you could use this environment, this area also. There's also space on the other side that belongs to CERN. And we could have something like 10 to the 13, 26 GB protons in a short few nanosecond pulse, which allows us to produce a very high number of muons. Not as many as we would have in the rear collider, but coming close within an order, I mean, about an order of magnitude only different. Okay, and because this is MOLAS, there's no problem with groundwater radiation, so we could actually have a 4 megawatt target in there if we were able to produce the beam at 4 megawatts. Just to give you an idea that this is not all just plans, we started some work, for example, on the power converters. Here you see different excitation lines from the power converters. And we would like to have something that's like a sawtooth, but for the power converters, something sine-like is best. And so we will have to identify what's the best compromise. By using different frequencies, we can actually produce something that becomes very linear, but then it will be more costly than if it's more sine-like, and obviously with beam dynamics and so one has to find what is the proper compromise. On the RF challenge, there have been some studies of the beam loading at the high energy, and we started to look into also with INFN actually into collective effects just to see they're there, but this is all just starting. We also started to look into the neutrino flux. You see here a map where the direction of the detector is in this plane here, and the horizontal you see the x-axis of the plane of the collider, and the vertical is the vertical of the collider. And you see here the neutrino flux. And there is here around the experiment, that's something we have to work on with the experiment. But there is, for example, this is from the US lattice, some sort of higher neutrino flux in some area there where it probably shouldn't be. We would like to avoid that, so that has to be designed out. And then there was some first study using Fluka on the actual losses of the electrons and positrons in the collider ring. And you see here a simulation where we have some shielding inside and the magnet, and you see the losses, the distribution within the magnet. Okay. Before I conclude, I would just like to mention some alternative scheme, which has been very useful and very interesting, which is the Lemma scheme, which has been developed at NFN, mainly by Pantaleo, and with lots of support from others, which had a brilliant idea, where you use actually a positron LINAC to maybe a ring, and you shoot the positrons at 45 GeV or so into a target. Then the energy of the positrons with the electrons from the target, center of mass energy, is high enough to produce a muon pair. And so you can produce muon pairs with a very small emittance, some 10 nanometers normalized. And then what you do is you collect the muons in a ring and send them through the target multiple times, maybe up to 2,000 times. And by that, you accumulate a more and more intense muon beam, still with a reasonably small emittance. Unfortunately, the emittance increases with each turn. So that is a great scheme. The one problem is that nature is a little cruel to us, because in this process of pair production, there is an alternative to that, a competing process, which is Bremsstrahlung, and which has a cross-section that's about 100,000 times larger. It's 100,000 times more probable to lose 10% of the energy due to Bremsstrahlung. And so the energy cost to produce a single muon pair here is of the order of a millijoule. So the current has to be low in the collider. And that means we have to compensate by a very, very small emittance. And then unfortunately, this multiple scattering leads to some emittance growth. So the only way to achieve a small enough emittance, a high enough brilliance of the beam, is to produce many muons per shot, per positron bunch. And then you can calculate that the charge in the positron bunch needs to be very, very high. So for a 3 millimeter beryllium target, we talk about 10 to the 15, a few 10 to the 15 positrons needed in a single bunch. And you need then a train of bunches in the target for that. So this is very unfortunate. And it may be possible that there is a game-changing invention that can recover the scheme and make it something that we could really put in as an alternative. However, in the moment, I don't know. It needs some clever young person to come up with something that we don't think about right now. There is an alternative also proposed where Bethe-Heitler production of muons should be used. However, we have to look into that. At the first glance, it may also have some issues with getting the density of the muons in the bunch. So in conclusion, the muon collider is a unique opportunity for high energy, high luminosity lepton collisions with a high luminosity to beam power ratio, hopefully, and cost efficiency verified. So we are optimistic, but we have to see. We mainly consider two options, 3 TeV and 10 TeV. And it's clearly not as mature as IC or Click, with important R&D to be done, but with no showstopper, as far as we know. And so now we want to bring it to the maturity level that the next European strategy can make informed choices in what they propose. And here there's a link. I would like to actually thank the muon beam panel that helped with that. So it's formal body, the collaboration and the formal collaboration, the old map study and the mice collaboration, and obviously the Lemma team and the others. So thanks a lot. Okay, is there still anybody? Hello?
Oh, thank you very much, Daniel.
Sorry, I started to worry about.
Yeah. We were muted to listen you more carefully.
Yeah,
okay.
Yeah, no. Next time I hope I will be able to come. Times would improve.
Other questions? There's one question here from Pierluigi.
Yes, hello, Daniel. I have a question on your scheme with the slide in which you show the layout of this muon collider. The accelerator ring can be the one, or must be, let's say, the one of LHC?
Yes. Yeah, I think for a 3
This one, yes.
Yeah, for a 3 TV collider, we would need an optimized ring of maybe 14 kilometers, or we could use the LHC, in which case this trick of having superconducting and normal conducting magnets together could be avoided. We could only use normal conducting magnets in that case. So the LHC is good for up to 6 TV for that. So clearly the LHC tunnel can be used for this. We think it's hard to use the LHC tunnel as a collider ring because of the neutrino flux, because you have these straits and they point to places and you cannot change that so easily. So we have to investigate that. But as an accelerator tunnel, we think that it's very likely that we can overcome the problems. Absolutely.
Thank you very much.
Okay. There's another question. Just a second.
Sorry. Could you explain, I just lost, what is the mover system to mitigate the problem of the neutrinos? What is mover system?
So it is, well, the movers themselves, what is the best technology? We will have to see if it can be piezos or if it needs to be stepping motors or so. So the magnets, the whole beamline would put on supports that can be moved. The beam itself is moved by dipoles. So we would need to add some dipole coils within the magnets to get the vertical deflection. So we need roughly 1% of the horizontal banding to achieve this, to achieve sufficient vertical banding for our purposes. I don't know if this answers the question. So one of the challenges we certainly face is to have a large range mover system that can do stably small steps. However, the beam will do maybe smaller steps than the mover system. So the mover system doesn't need to follow all little changes of the beam. It just needs to adjust. If the beam moves in a significant way within the aperture, then we need to readjust afterwards with the mover system externally. Maybe.
Okay,
I don't know if this is a question, sorry.
Are there other questions? If not, let's thank the speaker again. Thank you, Daniel.
Thank you.
Okay, let's move to the next talk. The speaker is Pantaleo Raimondi. Everyone, at least here in Frascati, knows Pantaleo. Pantaleo has been the director of the accelerator division for many years, and after that he moved to European Synchrotron Radiation Facility, when he managed the project of the upgrade of the machine. He's an expert of collider, lepton collider, but also an expert of synchrotron radiation machines. So he's going to talk especially on this topic. So Pantaleo, it's a pity not having you here, but at least we can listen for you. Can you show up?
Hi, good morning to everybody. So can you hear me?
Yeah, very well.
Okay, so, and yes, I think for the COVID emergency, it was very hard for me to come at Frascati at this time. So I hope there will be better occasions. So if you want, I can start to share the screen.
Yes, start sharing.
So can you see the screen? Can you see my screen?
Yeah, go into presentation mode. It's okay. So you can start. The floor is yours.
Okay, thanks for the introduction, Alessandro. And the topic of the presentations are really dedicated to the next generation, let's say, or to the future of continuous progress on sources for synchrotron radiation, X-ray based science. So I will give you a brief introduction on the topic, and then I will describe at length basically the optic related to this kind of machines, and also how we can build better and better performing machines, and then a few conclusions. So I think, again, I hope that people are familiar with these topics, because I know that this is really light source oriented, and for basically all the synchrotrons that have been operating for X-ray science have been designed with this double band achromat optic that definitely has been extremely successful and led to the creation of many facilities, and is still the most widespread used lattice. Obviously, now people want to have even more performing machines, and many studies have been performed, and few machines have been built with many dipoles, multiband achromat rings. And I think Max 4 was the first one, and then we had finally EBS and Sirius, and many others are in design or construction worldwide. So the hybrid 7-band achromat, I will describe it momentarily, has been proved very effective in addressing the nonlinear dynamics challenges associated with pushing the emittance down, so by a factor at least 30 with respect to the double band achromat. And however, still, even with this 7-band achromat, we are still not we are close, but not yet there to the long sought diffraction limit regime, where actually horizontal emittance is effectively of the same order of magnitude, or maybe lower, than the natural emittance of an X-ray beam. So if you can get an horizontal emittance as small as basically the wavelength that you are producing, then the source will be fully coherent transversely. So I will show you how this can be done really on following basically the path led by the 7-band achromat at ESRF. So this is the current portfolio of performance portfolio of many rings. They are not all here, the existing one. There are many more, but here are mostly just light out the one that are either have been just recently built, like Max 4 and Sirius, or all the others that are undergoing an upgrade, like EBS. So you see that ESRF EBS is the first one actually of this kind of upgrades that has two blobs, of which one is gray, because this machine obviously has been decommissioned and now is operating with lower emittance. And you see that actually what is laid out here is the circumference of the ring and just the raw emittance of the ring. And you see that actually, surprisingly, all the emittances of all these rings, they are all very similar. And now, regardless of energy or circumference, and now the trend is to push this average value at least a factor 20-30 down, like has been done at EBS. EBS has been the first to do this. And but also you see that the size of the blobs actually there are a little bit more data in these plots. I put as size of the blobs the transverse acceptance, the dynamic aperture of the ring, and so this is for reference is a dynamic aperture of 10 millimeter, and the color of the blob is related to the lifetime. Lighter color means a longer lifetime. And you can see that all the upgrades basically are trading off these other properties of the ring that are essential for delivering a very good stable beam to the users. They trade off these quantities for emittance. And if the dot becomes too small, so if the dynamic aperture is lower than 5 millimeter, you cannot even accumulate anymore, but you have to adopt swap up techniques. So similar, LHC does the same thing at the end. So when the current decreases below some threshold, the beam is dumped and is put a fresh one. So those are really what it would be nice to achieve in order to really reach a diffraction limited source. So the emittance should be another factor 10 smaller with respect to what has been achieved by ESRF and what is been planned for all the upgrades. But when you do this, you have also to play some more games. So here in the presentation, I will show many optics things. So, and I know that Frascat will love this, at least all the accelerator group. So maybe the others will be a little bit bored by that. So what also you need is when you reach this diffraction limited regime, you have to make sure that the electron beam is matched to the X-ray beam. So this means that beta functions into the insertion device have to be equal to the half of the length, roughly, of the insertion device itself. So, and obviously, in order to operate comfortably, you want to have a very long Touschek lifetime, very large dynamic aperture, and you want to be able to operate with ondulators with very small gaps. So in order to really have the maximum out from this beam. So these parameters, if achieved, will allow operations very similar to what has been currently achieved. And that was one of the key ingredients of the success of the double band achromat. And that's why we have so many facilities running around the world. And this obviously means translated in the relaxed injection complex requirement, beam stability during injection and costing. You can have many modes of operation of the machine, multi-bunch, you can put single bunch, hybrid with high current single bunches and multi-bunch, and so on and so forth. And obviously you will have a very, say, green-like facility with comfortable radiation handling. This is really like, for instance, SRF is a very good example. It's one of the best examples for that. And then many other advantages, in particular reduced component activation and insertion device radiation damage. This is a big deal because we see definitely, even on the old machine at the SRF, that many insertion devices have been degraded. And for this kind of very high performance machine, you need the insertion device not to be degraded at all, otherwise you are going to spoil the advantage of the low emittance beam. And obviously, you want also to have this reduced operation cost and work plug power. So I will show you a very simple path actually to get this factor 10 without very conservative path. So first of all, it would be nice if a hybrid band achromat can be pushed in order to have an equilibrium emittance a factor 2 smaller with respect to the 7-band achromat. So this brings the emittance to this kind of values. Then if you make a layout consistent with the implementation of wigglers, of Wigglers, you can reduce the emittance by another factor 2. This is very convenient, actually, for the multiband, for the hybrid band acrobat. And unfortunately, for EBS, we could not take advantage of this other property. So the hybrid multiband acrobat has, thanks to the fact that it has a lot of very long and weak dipoles, has a very reduced energy loss per turn due to synchrotron radiation. So this makes it very favorable for the implementation of Wigglers, that they don't have to really add that much in terms of additional energy loss in order to lower the emittance. So definitely on a green field, you should take advantage of this other property to get this other factor 2. And then at this point, you can couple the horizontal vertical plane and to share the horizontal and vertical emittance. And in this way, you will gain another factor 2. And then the vertical emittance becomes equal to the horizontal. This is possible only when the horizontal emittance is just a factor 2 larger than the desired vertical emittance. So the desired vertical emittance obviously will be either the diffraction limited one or the one requested by the users. But we are talking about, fortunately, about the same values, around 10 picometer. And then you want to have additional dedicated sections for optimal injection and flexibility. And obviously, when you have all these insertions, you have to delimit as much as possible the drawbacks due to the reduced periodicity of the lattice. So those are basically very simple ingredient, and I will show you that it's, at the end, it's a very conservative approach, but brings you where you want. So we spend just a few words on the 7-band achromat. So this is double-band achromat. You see 2 dipoles and some optic. This is, again, the 3rd generation layout for the sources. Max 4 is the first one that has implemented a 7-band achromat. So the emittance roughly goes down with the 3rd power of the number of dipoles in the ring. So that's why you gain quite a bit going from 2 dipoles to 7. And obviously now the dispersion gets very small, beta function gets very small, and the sextuples, in order to correct the chromaticity of the ring, they get very, very strong. So for the hybrid multiband achromat attacked this problem, and they solved in this way. So you create 2 large bumps in the beta function and in the dispersion in the ring, and you place the sextuple only in these locations. In addition, between these 2 locations, the sextuple are in phase, basically, at minus psi, and the geometric aberrations introduced by the sextuple do cancel completely. And the very interesting thing is that the sextuple, they get very weak, and actually need even less sextuple than in the double band achromat, only 6 instead of 7. And this I mentioned already. And also, since you have very small KRH, even the intrabeam scattering is largely reduced. You see also that, surprisingly, the natural chromaticity of this ring is of the same order of magnitude, actually in the horizontal, even lower than the former double band achromat. This is really striking. So for ABS, this is really then what is being done, and again, has been possible. You see, this was the former machine, only 2 dipoles. Somehow you are able, thanks to the to careful engineering, say super engineering, to put in the same length many more dipoles and many more elements. You see that are much more compact, and the system is very much more optimized, like a Ferrari. So I want just to show what happened for the former machine on ESRF. I think Francesco, the director, will love this image. So this is the old ring when it's been fully disassembled. And actually here you see that all the elements are slowly going to be surveyed in terms of radiological activation and disposed of. And this old machine has been replaced by 32 of these arcs, so that are each one 22 meters long. So just to show you that this machine worked very well, we had set up a set of parameters for the machine that had to be achieved in some dates in order to allow both the recommissioning of the machine, the commissioning of the new of the beam lines, the recommissioning of the beam lines, and the start of USM operations. The USM operations were scheduled to be started, say, last year at the end of August, and we had a goal of parameters to be set, but these parameters actually were achieved many months ahead of August 2024. And finally, the design parameters of the machine that we thought that could have been achieved actually after another year were achieved more than 1 year in advance. And I want just to mention, again, this is a Touschek celebration, that for this machine, we were able to reach the Touschek lifetime computed for the perfect lattice with no errors, estimated to be around 40 hours. We were able to reach this value in 2021. So in 2021, the machine is delivering a beam with a Touschek lifetime equal or even slightly larger, thanks to the polarization, than the one foreseen for a machine, a perfect machine with no errors. So I would just say that you can definitely conclude from this then that EBS is a very conservative design, and I want to add, very well engineered. So just to see, show what you gain in terms of performances with this machine. You see here what is the kind of spectrum that you had. So the green and the blue and the red are is the spectrum from an undulator, 18mm undulator from the old machine, and you see actually that you hardly see the lines because of the broadening due to the large emittance. And with the new ring, you really start to see very sharp lines. So you gain actually you even gain even more in power at the peak, and the peak gets much narrower. And obviously you have corresponding increase in brilliance and in coherence. I want just to add that this line, the remaining contributions are related to the beam energy spread and to the number of periods of ondulators. And those are basically, at least if you want further decrease this width, you have a possibility is to try to improve on these parameters. So for the how to get to a more performing hybrid multiband achromat, just to mention that this is the optic of the 7-band achromat, and you have also the additional problem that the beta functions at the undulator level, they are not really well controlled and can be modified only by large change of the overall surface advance. And obviously you have to compromise these numbers with all the other parameters of the ring. So in order to attack this, you need more flexibility. In particular, you have to have an additional quad at least in order to focus the beam more properly in both planes. And these obviously all people that know well about optics, they know that you need really a triplet to do this, not a doublet. And so you have to add another quad. So, and the trick is to add a quad not right close to the first doublet, but a little bit further off, actually in the middle of the first dipole. This allows, no matter what, to control the beta functions at the ID that now they are both matched to the undulator length, but also further squeeze the emittance down, because you see that now the 7-band achromat becomes effectively a very compact 9-band achromat. And again, remember the scaling law of the emittance that goes with 1 over the number of dipoles to the third power. So this basically gives you a multi-band achromat that has over emittance by factor 2, what you want, and actually has very little very little detrimental on performances. Actually, some performances are even better than 7-band achromat, but I'm not going to describe this, otherwise I need 2 hours. And I want just to say that all the optimizations and the lattice that I will show now, they are being done considering the EBS engineering. So all these things, the lengths, the size of the magnets, the distance, and so on and so forth, are identical to the one that we made for EBS. So all the lattices that I'm going to present, they can immediately say be rebuilt, and they will look like the physical hardware that I've shown you for EBS a few slides ago. And and definitely these machines can be built identical like has been done for EBS, and there are absolutely no components in the critical path. When you put all these constraints for a 3GV ring, this ring is 23 meters long, and you cannot do very much about it. And so you can further optimize the 9-band achromat with the numerical simulations, with numerical means, and you see that you can gain even a little bit more in performances in terms of dynamic aperture and local momentum acceptance. So this is the black line, is local momentum acceptance along the cell length, and you see that you can slightly further improve it by simply numerical optimization by a few percent. We're talking about 10–20%. So you have, as I mentioned, you have to have also dedicated section for optimal injection and for the wingless. So what you can do is to have an injection cell very long, where you can push up the beta functions, and in order to have very good injection efficiency, and then dedicated cells with longer straight sections for wigglers. So this I'm not going to spend too much time, but on this because the topic is very long. But when you put these long insertions in the ring, you have to make sure that the overall performance of the rings are not spoiled by the breaking of the periodicity of the lattice. There are a set of conditions that have to be satisfied. I'm not going to go through these, but just to show that there are many conditions that have to be satisfied, and you have to have enough degrees of freedom, enough elements, quadruples, and so on and so forth in this section in order to meet all these conditions. This can be done, and actually has been done. And I will show you the performances momentarily. So for a greenfield region, then optimized in this way, you go from a full periodic ring, say 24 cells, to a ring that has the 24 cells, of which one is very long for the injection, 5 are longer than the standard one, and you have wigglers on them, and then the remaining sections are dedicated for the users. I will show you actually these few examples, but just go through the blue line to the yellow one, that is the full ring with all the other long straight sections inserted, and you see how the performances are degraded, and the degradation is very moderate. In particular, the dynamic aperture hardly degrades when you insert the long straight sections, so go from blue to yellow. You see the horizontal aperture is hardly unchanged, and the local momentum acceptance also is decreased by about only 25%. 25% in local momentum acceptance is a very small number, so we are very happy for this. But just to show you how affects the Touschek lifetime, 25% the local momentum acceptance decrease corresponds to factor 2 to decrease in Touschek lifetime, because this Touschek lifetime goes to the third power, 1 over the local momentum acceptance of the ring. So you have really, you don't have, you can lose very fast in Touschek lifetime if you don't play this game carefully. As you can see, this ring, when you put all these long stretch sections and wigglers on, delivers an emittance of the order of 15 picometers and a lifetime, Touschek lifetime of the order of 65 hours. You can also see here, this is very striking, that if you operate in flat mode, you don't couple the horizontal and vertical plane, the Touschek lifetime is 18 hours. In theory, it should be the same also in the round beam mode, because the overall area, the volume of the phase space is the same. But then you have instead 65 hours, not 18 anymore. This is because you see this plot on the left side. This is really striking. So everybody knows that lowering I want to spend a few times on the Touschek because this is the celebration. Everybody knows that when you lower the horizontal emittance, the Touschek lifetime decreases, and is this. But this doesn't go on forever. At some point, actually, the lifetime starts to increase again. This is a very simple effect, actually. I thought it was not immediate to realize it, that at some point, if the emittance gets very small, actually the effective energy that you can transfer in the longitudinal plane becomes smaller and smaller. So if the angular divergence times gamma is smaller than the momentum acceptance, so these electrons, they do Touschek, but they never get a delta energy larger than this value, so they are never lost. So this is, but in order to do this, you have to have a very large momentum acceptance and a very small emittance. So, and this is what you start to see here. And I want just to say that TBS is the first one, the first machine that starts to see this. This actually is why also the lifetime of TBS is very comfortable, because he is already in a regime where you see these rays. And obviously now we are at the turning point, and from now on, let's say, if you build this multi-band achromat and better performances based on this approach, you will have Touschek lifetime progressively larger. And just to say that for SSRL-X, that again is the upgrade for SSRL, so I did not mention that it's been looked at the Slack. So this Touschek lifetime is larger than what SSRL has now has about 5 hours with an emittance of 7 nanometers. And here you go to 65 hours with emittances of 15 picometers. And I want just to also say that the Touschek scattering will not be a nominal effect on the lifetime anymore. So for large facilities, it's not easy to design a lattice that preserves good dynamic aperture and local momentum acceptance, because the dipole becomes very weak and sextupole very strong. So I want just to say that for Petra 4 and PEP, actually this is a large ring at Slack, you can foresee an upgrade very similar. So Petra has 8 arcs about 200 meters long and 8 long straight sections of the order of 100 meters. And 4 arcs will be dedicated to insertion devices. Then 4 arcs will have wigglers in them. And then you have a straight section dedicated for injection and RF. PEP layout is very similar. 6 arcs and 240 meters and 6 long straight sections. So for these rings, you have very weak dipoles, so you have to do something else. So what you do is that instead of having actually a 7 or 9 band achromat, you go the other way around. You have only 6 band achromat. In this way, you can have a much larger dispersion and still very good control on the sextile strengths and the nonlinear optic. The trick actually has been to remove the photolattice in the middle of the 7-band achromat and just have a triplet that ensures the minus psi transformation in the both planes between the sextupoles. It's a very simplified going down from the 7-band or 9-band achromat to 6-band achromat. So, and then you have very long straight sections, and again, you have to play this game with the transparency conditions in order to not spoil the performances of the not periodic, not full periodic lattice anymore. And this is actually for the injections. Injection section is very long, and you can actually put two large point, one for injection and one for beam abort. I just want to say that thanks to this large beta functions at the injection that is not really needed for injection efficiency, what happens is that the injected beam oscillation is greatly reduced thanks to the magnification of the beta functions. Here, beta functions is about 40 meters. At the ID, the beta functions are of the order of 2 meters. So there is a natural decrease of this distance by a ratio, the square root of the ratio of the beta function. So you see that even when you inject the beam at the septum level, this is the stored beam, this is the septum thickness, and this is the injected beam, what happens is that all the electrons do oscillate at the ID level within a ring of only 2 millimeters. And so this means that you can comfortably put insertion devices around the central trajectory in the straight sections with gaps very close, very small in both planes, both vertically and horizontally. So needless to say that all these rings have an injection efficiency of 100%. You see here actually, this is to zoom. I don't know if you can see it, but this is the same thing zoomed out, where you see actually where is the dynamic aperture. This is way infinitely larger of what is required in order to have good injection efficiency, but is required in order to have to be able to operate with gaps very small in both planes in the straight sections. So just to show you, this is the same comparison made. You see here that all the comparisons between the, say, full periodic lattice, say the blue line, and the yellow one is the lattice where you have all the straight sections included. And you see the degradation in terms of performance. So you see that there is non-degradation in the dynamic aperture, and again, a degradation in the local momentum acceptance, again, of the order of 20%. When you have these very long straight sections inserted. So definitely we can do it. And same thing like for SSRL, you have Touschek lifetime of the order of 100 hours, whereas for Petra with an emittance of 1 nanometer, Touschek lifetime is less than 10 hours. So you can do the same thing in the PEP tunnel. Again, fortunately, we have these very large rings around the world that you would not really build probably up front for a greenfield machine, but you can use what you have. And by chance, they are really almost very much the best that you could want to do. And so as well as I mentioned, for the 6 arcs for PEP, 243 meter long, you can put 12 of these 6-band achromats. And then some of the arcs will have insertion devices, some will have wigglers in the straight sections correspondent. You see how does it look, the lattice in the straight sections, 123 meter long. You can have very nice photo lattice there, or also dedicated section for the injection, as I mentioned. So this is how does it look for PEP, the optic. You see, these are the arcs and those are the straight sections. And you can get emittances of the order of 8 picometers in both planes with energies of about 5 GeV. And as I mentioned, with unprecedented characteristics in terms of dynamic properties and beam stability. So I want to also launch a stone on a possible implementation of a 9-band achromat at Frascati. So it's done a very preliminary exercise in to rescale the 9-band achromat to an hypothetical ring that can fit in the Daphne hole. So, and again, the goal of the exercise is to see what kind of parameters can be delivered by a synchrotron radiation X-ray source at Frascati, given the site Given the site and existing facility constraints, the study has been made just for a ring with an energy of 1 GeV. You can change this as you want, and a circumference of around 110 meters. I think is very much the maximum that you can put in the Daphne hole. So a ring with 8 of 9 hybrid 9-band achromat cells that can match these constraints can deliver indeed a very, very small beam. And again, I want to mention that the element dimension is made considering the ESRF EBS engineering. So if you build 8 of the 9 cells, they will look like exactly like the one that I've shown for EBS, actually identical. Right? We just have to rescale linearly the dimensions of the magnets. So, and what you get is, supposing a ring energy of 1 GeV, a circumference of about 110 meters, and of these 8 cells, 6 can be dedicated to insertion devices, 1 for injection and 1 for RF. You get an emittance surprisingly very close, almost identical to the one that EPS has at ESRF, but this is 1 GeV, it's not 6 GeV. And very nice other properties, actually. Those are better in the longitudinal plane. The energy spread is almost is 2.5 smaller than what you have for EBS, so it's very small because the low energy, and also at zero current, a very short bunch length. So, and I want just to say that this source obviously has full transverse coherence up to 1 kV photon energies. And again, there could be a window of interest for users working in the IR that like is currently used at Frascati, but could go even up to 1 kV or close to it. And obviously for this, you need short period CPM use, cryo permanent magnet ondulators, and use at that to be used also at higher harmonics. But again, this I'm just launching a stone, not going to discuss it further, but this is up to you, that you can take these numbers and see if it's worth to study the issue further. So I just replot the synchrotron portfolio performances with this kind of machines that I just described for the upgrade of SSRL at SLAC, and these large facilities, how they could look like. And you see really from this that we are talking about a complete new, at least another factor 10 with respect to what is currently either achieved or under construction at the moment. And this definitely brings you to the long sought diffraction limit while keeping or exceeding actually all the other double band achromat. This was thought to be impossible. So I want just to also mention that, as I said, the emittance of the ring is scales with the cubic 1 over the number of dipoles to the 3rd power, but not the number of dipoles to the 3rd power in the cell, but the number of dipoles to the 3rd power total in the ring. So ESRF has 224 dipoles. SSRL has the same kind of number. That's why the performances are very similar. And but then this you have to rescale with the energy that this is a 3.5 GeV ring, and also as the addition of having wigglers in it to push further the emittance down. These kind of rings, actually, they have 400 dipoles, so they are intrinsically 8 times better than ESRF, basically, because they have twice the number of dipoles, and as I mentioned, you have to things improved to the 3rd power. So intrinsically, they are 8 times better, and then since there is a space for wiggler, and you can play the trick of coupling horizontal and vertical plane, you can get another factor 4 in addition to this. I want just to show that this circle is the 6-band achromat with 8 cells, and is a circle that is here. So this is not negligible. That is in line actually with all the previous, the other upgrades that are being made, but with much smaller and probably cheaper ring. But still you get this, and you can still play the trick of coupling horizontal and vertical emittance, because definitely you are diffraction limit anyway. You can get down another factor 2 on this, so can even exceed all what is being made at the moment. I want to spend some last slide on something that is, say, for many is counterintuitive, and but this is a real fact. So as I've shown you, this is a cell, is 22 meters long for EBS, and it costs about 4 millions, this complex. After this complex, in the machine, there is the beamline. The beamline is nowadays is something around 40 and 150 meters, and it costs about something between 5 and 20 millions. So this is the cost of the experiment. This is the cost and the size of the source. So the hybrid multiband achromat is a very compact accelerator, because this is the hybrid multiband achromat, and has very favorable accelerator size to experiment size ratio. This is less than 1, maybe around 0.5. Accelerator cost with respect experiment cost ratio, again, way less than 1, say about 0.5. And accelerator operation cost to operate this with respect to experiment operation cost ratio. Again, those are all true facts. The only drawback, so this is one accelerator and one beamline. This is. So the only drawback is that this accelerator cannot operate alone. Requires that you have to operate many of these simultaneously. They have to have all linked together and help each other somehow. This is the difference. And requires, you cannot build only one of these in order to have this thing and this thing, but you have to build many of them, so, and they have to operate simultaneously, something around, as I said, 10, 30. This has the drawback, say, call it drawback, but at the end is an advantage as well, that large facilities or factories have to be built, where many beamlines must operate simultaneously. It has to be noted that up to today, this research field is very rich, and such facilities are largely overbooked anyway. So it's not that you build something with 30 of this because you have to have 30 of these things in order to work, and then many are unused. This is not true. Actually, all of these are largely overbooked, and you want more and more. That's why actually we are building more and more machines. And it is foreseeable that with new sources even more performing, it will continue to be so for many years to come. So at the end, this, from what I know, is the most compact and cheapest source of X-rays for a given beamline that exists at the moment. And this is true for everything, including all the possible combinations, FEL or inverse Compton scattering and so on and so forth. This is cheaper and smaller.
Pantaleo,
so I jump
to the conclusion. Okay.
So I jump to the conclusions, and again, as I shown, the accelerator scientific community is very active in order to produce a new generation of hollow emittance synchrotrons, and definitely is conceivable to push this at least another factor 10 in terms of performing, and we can definitely reach the diffraction limit. So thanks for your attention.
Thank you, Pantaleo, for these astonishing results that you have shown, and also for the stone that you have thrown that has hit us as usual. Okay, so now the floor is open for questions. Are there any questions? I have just one. Do you see any possible application of this concept also for colliders, or is you are in completely different fields now?
This actually I have taught as well, but again, this presentation was just oriented to light sources. So definitely you can conceive, again, say for Daphne, I'd say, to have this kind of lattice with obviously a low beta insertion built with the principle that I just stated in it, and you can get indeed probably a very, very high luminosity with very, very good lifetime at say again to have a very high performing phi factory. This you can do it. So if you want to talk just about that, definitely you can do it. Obviously, nowadays for this it would be only probably oriented to something to do Siddhartha-like experiment probably, but you can do it. So so definitely you can take advantage of this low emittance beam with this very good qualities to build something that is definitely 1 or 2 order of magnitudes, probably close to 2 order of magnitudes higher luminosity than what has been achieved with Daphne. I don't know if this answers your question.
Yes, we have also a question from the chat in this moment. Can you get it? There's a question asking if it is possible to reduce the natural emittance even down to 1 picometer with the H9BA.
If it was possible, I would have included I mean, if I had known how to do it, I would have put it in the slides. I don't know if this answered the question. I don't know how.
Not for the moment.
Yeah, again, with the constraints that I just mentioned, I don't know how to do it. On the other hand, I would counter question it. Why do you want to do it? Because at least for the synchrotron light, you are not going to see a difference. What the difference that you could see actually is if you can improve the longitudinal coherence, actually. And it means low energy and bandwidth, low energy spread, low bandwidth of the X-rays, and shorter pulses. So this is at least in terms of phase space for that is still missing, say, with respect to a pure FEL, an FEL with SASI, with seeding.
Okay, Panteleo, thank you very much. We ran out of time, but it was very, very, very interesting. So thank you very much for this contribution.
Thanks.
And see you in Frascati sometime. Okay, so we move to the next point, next topic of this afternoon session. We are having the naming ceremony for the visitor center of the LNF. I think that Leah wants to introduce this point. We have the honor to have here a member of the Touschek's family. So I ask Leah to give an introduction.
At the end of this day, which has seen all our community together between yesterday and today, we have the pleasure to have Francis Touschek, Bruno Touschek's son, to tell us a few words about his father and about the time that he were in Frascati. After this, we will move to the visitor center, where INFN has decided to dedicate a plaque to Touschek's, the visitor center to Bruno Touschek's name. Unveiling of a plaque.
Just to be precise, a few of us will move to the visitor center. I will call them personally. The other one can stay here because the ceremony will be broadcasted. And then after that, it will be a very short ceremony. We will have a toast just outside here for just to say chin chin for this ceremony.
Ladies, gentlemen, thank you very much for being here and for having spent the last few hours commemorating and remembering my father. I was telling Dr. Bossi earlier on that I feel very much an imposter. I'm not a physicist. I'm not a scientist. I have chosen a completely different way of life, as often happens in cases like mine, with a very popular, very interesting man as a father. Nonetheless, it has been certainly an honor to be my father's son, possibly not a fortune, but certainly an honor to be his son. And we are very close in the early days. I was born in 1958, and inevitably at the time in which my father's career was reaching a peak. And this peak was shared with most of his family. And I spent a lot of my youth together also with Andrea Ghigo, who I always have the pleasure of seeing only on these occasions here in Frascati. And we spent a lot of time here playing. Very simply, when I first came to Frascati with my father, the building of Adone was literally a sort of a building site. There was nothing else around it. It was open countryside. And here were my brother and myself, and frequently Andrea Ghigo and his sister Paola, and we would play with electric trains. It was the famous Fleischmann or Lemma. Some of you might remember these old train models. So in many ways, I saw the place grow. And all of a sudden, though, I mentioned it yesterday at the university, at the end of the 1960s, there was a dramatic change in my father's attitude towards Frascati. He came to Italy before, obviously, I was born in, I think, 1952. And the first 15 years of his life here in Italy was sheer bliss. He married a beautiful lady, my mother, Elspeth young Touschek, and they must have sort of enjoyed the incredible atmosphere of post-war Italy. You know, Italy after the Second World War had a sort of determined strength to come out of the sort of rather negative effects of the Second World War. And then, yes, obviously I was born, and then in 1961 my brother was born, and it was the heydays really of my father's life. At the end of the 1960s, I also saw it looking at the wonderful posters and the wonderful copies of my father's drawings out on the left-hand side. The famous Caso Ippolito occurred when sort of politics started being very much part of the scientific research world of Italy. And then the most dramatic part, I think, that affected my father's attitude towards staying here in Italy was the student revolution, which led also to a general strike all over Italy. Some of you might remember the white strikes that put a stop pretty much to the development and the completion of Adone in 1968 to 69, which highly frustrated my father and frustrated also a lot of the researchers that were here in Frascati, because they saw their extraordinary advancement frustrated and slowed down. So much so that very possibly sort of Italy was overtaken by other countries in their sort of specific topics. Now, there are inevitably a lot of anecdotes that I could sort of go on about, but I don't want to bore you in any way. But my firm conviction is to thank you all very much for having been here. I was at the university yesterday, and I will be at the academy tomorrow. And organizing this spectacular event yesterday, today, and tomorrow deserves a great round of hands. And I would love to so thank Lia Pancheri, Luis, and all the organizing committee, and Dr. Bossi as well. I am well and truly moved. And as I said, I'm not a scientist. I have chosen a completely different life, and yet my heritage is inevitably linked to that of my father. So thank you all very, very much indeed.
So we can go on with the ceremony. We can move to the visitor center. I am inviting our president, Antonio Zoccoli, who is here. I'm inviting Pierluigi, who is actually the father of the visitor center, because it's his idea that from his idea that the center has been built. I also ask Leah to come with us. Obviously, our guest, Francis, is Jack here with you? Okay, so obviously also Jack. And I ask Mario to come also, and Paola and Alessandro as a representative of our two divisions. So you can see that the ceremony broadcast here, it will be very short, and then we will have the toast just outside in the hall.
Ho ritrovato anch'io parlarne della l'ultima cosa che feci fu
Qua sostituivo nella chat sicuramente la funzione. Susanna.
Le due parole stiamo semiportugesi.
Purtroppo non potranno essere più.
Ah, no, no, è non comply. Ma prima di togliere volevo dire tu 3 parole, visto che poi ne avete dette tante altre. I'll say it in English. One of the lovely things about my father was he loved physics. He studied physics. He played with physics. And I think he transmitted that love so abundantly clearly to all his students and all his colleagues around the place. And quite honestly, in all my life, and I'm now, maybe 63, I've never met anybody like him. So my admiration is great, and my gratitude is just as great to all of you. And I mean, it's like a polish.
Thank you very much.
Thank you very much.
Sì, una foto sotto una...
Some of you already know, but this is my beautiful wife.
Okay. Okay. Okay.